Welcome to this modern data warehousing and engineering tutorial where we will be deep diving into each and every concept of data warehouse, and we will also cover all the important advanced data warehousing concepts which are really important from project point of view as well as interview point of view. Data engineering is not just about moving data from point A to point B, it's about the architecture, strategy, and knowing exactly why we moved from traditional systems to analytical powerhouses which we are using today. If you have ever been confused by the difference between data lake and a lake house, or struggled to explain SED type 2 in an interview, this video is for you. Today we are covering full-fledged data warehouse and engineering concepts. We are starting with the foundations of data storage and moving into modern architectures like Medallion framework and mastering the complete data modeling from star schemas to Snowflake schema. By the end of this video, you will even build a real world capstone project, which is a dimensional data model for a hospital system. I have divided the complete tutorial into 6 ultra rich modules. We will start with module 1 and 2, where we will cover the shift, why the industry moved to Lakehouse and the differences between Inmon and Kimball models. Then we will move to module 3 and 4, which is the bread and butter of data engineering. We are mastering data modeling here from third normal form to star schema, and we will deep dive into each and every kind of SCD types you will ever face in an interview. Followed by, we will be covering module 5 and 6, where we get the technical with CDC file formats like Parquet, Avro, and we wrap it all with a full-scale capstone project modeling a real-world healthcare system. With that said, let's begin. Imagine you are the CEO of a global coffee chain. You want to know, did your latte sales in London increase when it rained last Tuesday? In order to know that, you go to your IT team. They gave you a very frustrated sigh. Why you want to know that? Knowing it does exist in their databases, but it is currently a hostage data, and it is trapped in, let's say, 50 different operational databases and one database for every region. They are right now in multiple files, APIs, databases, and Excels. They are right now busy ringing up the customers. If you try to run a massive report on them, you will lag the registers and ruin the morning rush as well. This is the inconsistency gap. Your sales data tracks the lattes, but your weather data is in the third party API, and your market promos are in a separate CRM database. They don't talk to each other directly, so they are in silos. This is exactly why the data warehouses was invented. It is not just another database, it is a specialized environment designed specifically to solve these kind of challenges. Okay, welcome to this ultimate data warehousing tutorial where we will be covering all the aspects of data warehousing. Whether you are preparing for interviews or you want to master the data warehouse, this video will be your one-stop solution for that. Let's begin with data warehouse. A data warehouse is a central repository designed to store every single amount of data. Okay, every single amount of data is stored in the data warehouse, and it is used for reporting and data analysis purposes. Okay, unlike the standard databases that only handles your day-to-day transactions, a data warehouse acts as a single source of truth for business intelligence or reporting, even aggregates, suppose large volumes of data from multiple data sources like data source 1, 2, 3. So this is a place where we have all the data stored at a single repo. Okay, it acts as a single source of truth for your data. Okay, now let's take one more step and understand the difference between database and data warehouse. As now we know that database is more like handling your day-to-day transactions, and the data warehouse is a single source of truth to store every single bit of data from multiple resources like A, B, C, D, E, multiple, right? Let's understand what are the potential users for database and data warehouse. If we talk about databases, the potential users are front end users, application developers, operational staff, or customers. Okay, and if I talk about the users of data warehouse, those are the data analysts, data scientists, and business decision makers. As the databases are used by front end users, application developers, and operational staff, so we can't afford delays here, right? There is no window for delays. That's why, if we talk about the primary purpose of the databases are that these are optimized for fast real time data recording and management. Okay, this is also known as OLTP systems. Okay, similarly as data warehouses are used by data analysts, data scientists, and business decision makers, the primary purpose is that these are optimized for complex analysis, reporting, and BI. So this we call as OLAP. Okay, and in database, the system we called as OLTP. We will obviously deep dive into those in coming few minutes. Now, as we know, the primary purpose of both database and data warehouse, and as we just discussed, the primary purpose of a database is the real-time data recording. So, indeed, if I talk about the data, it will only store current live data from single source or specific applications, right? So in the same fashion as data warehouse, primary purpose is analysis, reporting, which we just discussed, which requires historical data as well, right? So it definitely is used to store historical aggregated data consolidated from multiple disparate sources. If we talk about performance, we know that in order to serve our customers, we need really very fast solution with very high speed read writes, correct? So databases are optimized for high speed read write operations on small set of records. Make sense? And similarly, in data warehouses, we need to scan tons of historical data to support reporting, right? So obviously data warehouses are optimized for high throughput on complex queries that can scan billions of rows. Okay, make sense? Cool. If we talk about the examples for databases that are MySQL, PostgreSQL, Oracle, Microsoft SQL Server, and so on. And if I talk about the examples for data warehouse, those are like Snowflake, Google BigQuery, and Amazon Redshift. That's pretty much about the difference between database and data warehouse. Now we know what is the database, what is the data warehouse, what was the problem existing which data warehouse solved for us, right? So we will obviously covering the next relevant topic and another important topic from the interview perspective, and which we was already discussing here, the OLTP and OLAP systems. The difference between OLAP and OLTP. OLAP stands for Online Analytical Processing, and OLTP stands for Online Transactional Processing. These both systems are integral part of data management, but they have very different functionalities. Okay. So if I talk about the differences, so I had divided them into categories. So first category, if I talk about the data sources, OLAP is the data source where we have all the historical data from multiple databases. We just discussed this, right? It is a single source of truth for me. All my data from any kind of source will be sitting here, right? And if we talk about OLTP, the data source is my current operational data. We also covered this part as well, right? So now let's talk about the purpose. We know that purpose of OLAP systems is to use them for analysis and better decision making and creating reports on top of them. And similarly, the purpose of OLTP is to actually serve the people, serve the front end users, serve my operational staff or customers. So it should be used for my day to day transactions, right? So what are the methods used? And obviously, OLAP is the method which we use in data warehouse, and OLTP is a standard for DBMS. Okay. And if we talk about normalization, we will also cover this in next 1 hour. In OLAP systems, tables are not normalized, but in OLTP systems, tables are normalized up to third normal form. Don't worry if you know that, that's well and good. If you don't know that, we will be covering in next 1 hour. Now, if I talk about the query type, OLAP system is very read heavy. It is able to query complex queries and all those things, but OLTP system is basically used to read and write the queries and just to use a simple queries. Okay, so that's why OLTP systems are very fast and OLAP systems are slow in nature. If I talk about the data volume, as we know, OLAP system stores all my historical data. So it actually makes sense to say that the data volume will be in terabytes or in petabytes. But OP system is only having my recent data, which is useful for your day-to-day transactions. So the size will be small compared to OLAP systems. Okay. If I talk about the update frequency, so we update our OLAP systems periodically by using batch loadings or by even doing OTL processes. And if I talk about OLTP, these systems are updated very frequently by users. This is something which is very user centric. So you can expect even updates every millisecond as well. So there is a possibility that might also be happening. Okay. If we talk about backup and recovery, it is something which we have periodic backup for that. We have multiple data warehouses like Snowflake, Big Google, BigQuery, Redshift. They do these backups. Okay, they have those features, and all OLTP systems backup we have to be doing continuous and rigorous backup. And if I talk about users, that thing you already know that OLAP systems will be used by analysts or your managers or your decision makers, and the users for OLTP will be operational staffs and customers and your main application users. If we talk about the focus, the OLAP system is mostly majorly analysis focused. Okay, that's why I had written here it is subject oriented. But OLTP system is more focused on operational parts. So that's why it is application oriented focused system. Now I hope that you know clearly what is OLAP and what is OLTP systems. Now, Jaswinder, I understand what is database, what are data warehouses. I even know the differences between them, and now I also know what is OLAP and OLTP system. Okay, we are keep on talking about all these data terms, which is cool. Okay, but now I have a question that, okay, we need to ingest our data into data warehouse. I agree with you, but you hadn't told us that how we get data into data warehouse at the first place. What is the process that we I am having multiple data sources, okay, and I am having database, how I will do and how I will handle all this data and ingest this data into data warehouse. What is the process? Okay, let's discuss about that as well. Okay. Now, as we just was discussing that on the left side, let's suppose we are having tons of data stored in tons of multiple sources like Amazon S3, SFTP, SQL Server, Salesforce, SharePoint, API, files, SAP, and many more systems. Okay. And on the right side, we have our very own data warehouse. So, in order to integrate or process data from multiple sources, storing it in a central repo such as data warehouse, we have a process. Okay, we have a process which is actually known as ETL or ELT. Okay, so if I talk about the ETL, so ETL stands for extract, transform, and load. Extraction is nothing, it's just the raw data which is pulled from multiple sources like database or your SaaS applications or APIs or sensor logs or flat files, blah, blah. So all these data we extract. So we call it extract layer. Then we have transform. Transform is where the extracted data is cleaned and reformatted in a temporary staging area. And common task in the transform include data cleansing, data deduplication, even standardization, or sometimes encryption. And third is load. The final clean data is moved into my target destination, such as data warehouse or even data lake, where it can be used for BI purposes. So the whole process is known as ETL, or ELT process is also there, where we first extract, then load the data, and then we, after loading the data into our data warehouse, we transform the data. Okay. If I go to the definition, ETL stands for extract, transform, and load. It is a data integration process, okay, used to collect the data from multiple sources, clean and organize it, and then store it in your central repo, such as data warehouse, for analysis and reporting purposes. Make sense? Cool. Now we know what is ETL or ELT. Okay. I will tell you one more thing, that we usually do ETL in layers. Okay. We don't just do it. We have layers defined to do the ETL process. Let's also touch base on these layers as well. So if I talk about the layers, first is my staging layer, and we can also call it extraction or landing zone. This is the initial or temporary storage area where my raw data is extracted from various sources, like we had just seen, like APIs, database, flat files, S3, SFTPs, right? It acts as a staging table to store the data before even it processes the data, allowing for validation without even affecting your source systems. Okay. So once we are good with our staging layer and we had extracted and landed the data in our staging layer, the second layer is known as data integration or transformation layer. This is majorly known as a processing layer, okay, and cleaning layer. And here the raw data is cleaned, filtered, or transformed into consistent format, and it applies all the business rules. Even we remove duplicates here, and even missing values also we handle here, and sometimes we even aggregate data. Every kind of transformation we do in this layer even joinings and missing data filtering. This is a transform logic that prepares the data for the data warehouse. Okay, this is the place where we do all your logic stuff. Okay, once this is also done, the final layer is known as access layer or core layer, and this is our loading zone or created data zone, and this is where we also create our data marts. Okay, and the final layer, the created data, all the created data is loaded into your target data warehouse like data marts for consumptions. So it organizes data into dimensional models. Dimensional models is nothing, it's just facts and dimensions. And don't worry, we will be deep diving into dimensional model in next 1 hour. It just organize the data into these dimensional models, and that organization is important for quick retrieval for BI tools. This is all about ETL layers. Okay, there is another variation of these three layers as well. Okay, in which we call the staging layer as bronze layer. Okay, data integration layer as silver layer, and access layer as gold layer. And this architecture is also known as Medallion architecture, and it is very famous architecture. Okay, now we understood, Jaswinder, what is ETL and ELT layers. We got the picture about OLAP and OLTP. We know database, data warehouse. Now you just introduced us to the new term, Jaswinder. What is these data marts? What is this thing? I don't know this. You just said it that the access layer is where you have data in your data marts, but what is data marts? Okay, let's discuss about the data marts. Data marts are actually nothing, it's just the subset of your data warehouse. Okay, it's just a small subset of your complete data warehouse, which is focused on departmental information. Okay, suppose you have finance department, and the data mart of finance department will only be having all the data focused for finance. So it is designed for a single department data holding. Okay, so data mart nothing, it's just a subset of data warehouse focused on a single department. Cool, let's discuss the definition as well. Okay, so data mart is a specialized subject oriented subset of a data warehouse focused on a single department or business line, such as sales, finance, or marketing. If you see this image, this is our data warehouse, and after our data warehouse we have these three data marts. And in data mart 1 we will be having specific data, let's say for sales, and in this we will be having data only for finance, and in this we will be having only data for specific marketing purposes. So these are nothing, these are just a subset of our data warehouse. While the data warehouse act as a central repo for an entire enterprise, a data mart provides a curated and streamlined view of data to improve query performance and accelerate decision making for specific teams. Because data marts are department focused, we are only having the department focused data, so obviously it improves your query performance and it accelerates the decision making. Right now let's understand about the another very important term, which is known as data warehousing. Okay, we know data warehouse, Jaswinder. What is data warehousing now? Okay, so if you remember this slide which you are seeing on your screen, we had just go through that in ETL part. Here we are fetching data from multiple sources, right? Doing ETL to load data into our data warehouse, correct? Then we managing the data into data warehouse. This whole process is nothing but data warehousing. That's it. Okay, the whole process is nothing, just a data warehousing. Okay, data warehousing is actually nothing but the way to process or manage or organize the data inside your data warehouse. Cool. Now let's go to the definition. Data warehousing is the process of collecting, organizing, and managing data from disparate data sources to provide meaningful business insights and forecasts to respective users. Make sense? Okay. Data stored in data warehouse differs from data found in operational systems. It is organized so that relevant data is clustered to facilitate your day to day operations, data analysis, and reporting. This helps determine the trends over time, allows user to create plans based on that information, hence reinforcing the importance of data warehouse use to business decision makers. This is what data warehousing is. It's nothing, it's just a complete process to manage and organize data. That is known as data warehousing. That's all. Okay. Now let's discuss about very interesting another relevant topic which is known as acid properties. And as you can see on your screen, acid stands for atomicity, consistency, isolation, and durability. So, what is atomicity? Atomicity means a transaction is all or nothing. Okay, either all its operations is succeeded or none are applied at all. Okay, if any part fails, the entire transaction is rolled back to keep the database consistent. This is known as atomicity. Either the transaction happens or either nothing happens at all. Okay. Okay. So if I have to put in a very simple words, I will say with atomicity, if any part of the transaction fails, the entire process is rolled back to its original state, and no partial changes are made and even not allowed. Cool. This is about atomicity. What is consistency? Consistency in transactions means that a database must remain in a valid state before and after a transaction happens. A valid state even follows some kind of rules like constraints and relationships. Okay, if a transaction even violates any of these rules, okay, then also it is rolled back to prevent corrupt or invalid data. Okay. What is isolation? Isolation ensures that transaction runs independently without affecting each others. Okay. So changes made by one transaction are not visible to others until they are committed to the systems. Okay. This is known as isolation. Fourth is durability. Durability ensures that once a transaction is committed, its changes are permanently saved even if the system fails. Okay, the data is stored here in a known volatile memory. Okay, so the database can recover to its last committed state without losing a single bit of data. Okay, that's why it's written permanent changes after commitment. Cool. This is pretty much about acid properties. Now let's discuss about very interesting and very famous topic, Kimball and Inmon data architectures. Okay. Kimball and Inman represents two foundational opposing philosophies in data warehousing. Okay. If let's review them and start with our Inman data warehouse architecture. Bill Inman is also known as the father of data warehousing. Okay. And he gave a top down approach, okay, which focus on enterprise wide areas. Okay. He advocates that we will pull data from sources, okay, and then we will normalize the structures for low redundancy, and then only we will store that data into our enterprise data warehouse. Okay, and this normalized data we can further use to feed our data marts or for reporting purposes. Okay, the best part of this data model is that it is very easy to maintain due to less data redundancy, but it has a higher initial cost and longer development times. It contains very isolated data marts. If I simplify more, Bill Inman suggested to pull the data, okay, and then normalize your data. Once your data is normalized, okay, store the data in your enterprise data warehouse, and then on top of your enterprise data warehouse is create your data marts and use those data marts for your reporting purposes. Okay, but uh, there are pros and cons for every systems. As you know, the biggest pro for this was, as the systems are very normalized, so it was very easy to maintain because there was very less redundancy across. But as it is normalized, the biggest con was it is having very high initial cost, and it took a lot of efforts to develop the systems. And even after the systems are developed, the data marts are very isolated because of this level of normalization. Okay, and there is other theory which was advocated by Kimball, which is just opposite of this Bill Inman theory. Before going to that theory, when we should choose the Inman data warehouse architecture is when you need a single consistent version of truth for the entire organization and have time for structured or enterprise wide approaches. Cool. Now let's discuss about Kimball. As we just discussed that on the opposite, Kimball uses a bottom-up approach. Okay, it means that we will be developing our dimensional star schema data marts first for faster business-driven user-friendly reporting. Where, as you just listened, that Inman said to use normalized structures, Kimball is saying to use dimensional structures. Okay, Kimball uses dimensional denormalized models, where Inman is saying use normalized models, Kimball is saying use denormalized models. Okay, this is very important to note. Okay, again, this is also having pros and cons as all the systems are having. The best part of this model is it is generally faster to implement and very cheap to start. Okay, but the con for this was it can be more complex to manage over times as the marts scale up. Okay, so if I talk about when we should use the Kimball, it is best to choose when you need to deliver business value quickly, focus on specific departmental needs, and or need an easy to use analytical models. Let's now discuss about another very important concept, that is normalization. Normalization is the process of organizing data to reduce redundancy. Basically, we want to make sure every piece of data is stored in exactly one place. No duplicates or no mess should be there in our data. Okay. If I go with the definition, so definition is saying that normalization in data warehouse organize the data to minimize your redundancies. Okay, this is the definition of normalization. It is the process to organize your data in order to reduce your redundancy and eliminate your update, insertions, and deletion anomalies by splitting tables into smaller related entities. It is better for OLTP databases. This is not something we generally use in OLAP systems as a data engineers. This is something more of like a database work, but you should know about normalization. That's the main intention here. So let's understand this by an example. If you see this table, in this table, there are a lot of problems. There is a person named John. Yeah. In first order, he bought two books. Okay. And in second order, he bought one more book. Okay. That's good. He is learning. But what's the problem here? The problem here is we are repeating the details of John Smith. Okay, we are repeating his customer email, we are repeating customer address. Now, suppose he is very hardworking and he bought 100 more books at different time. So, will you be doing 100 entries into this table? Will that make sense? We will be just increasing our storage cost unnecessary, right? Why we need to do that? Why someone will do this kind of thing? Because he don't know what is normalization. That's why he will do the 100 entries in this table, right? So there is one more problem here. if you see Robert and John, they both had bought the same book. Now again, you had started repeating the same story of storing the redundant data. Now assume the third scenario that John Smith had changed his address. Okay. Earlier his address was 123 Main Street. Now he had changed address to somewhere else. Now we need to do this change in multiple rows. Again, if he in future changed his email, then again we need to change that in all the rows, right? For every customer, don't you think we should be having only one entry so that any change we can incorporate in the same entry, right? So this is another problem. There is one more problem here. Okay, you just created a single table, a very big table. You created a very single table, which is also known as OBT, one big table, and all the things are inside your one big table. Okay, in same table we are having customer data and we are also having the books data. Okay, now you can't add any new book here without associating with the customer. Right. Now let's assume you have to delete the data of a customer. Let's assume you want to delete the data of Mary John. But now you are only having one table. So in the same table, you are having customer data and you are also having the book data. And if you removed the customer data, if you removed this entry, you will automatically lose the book details as well. That's why this table is not a great way to store the data, and this is unnormalized table. Okay, so sir, then we should divide this table into multiple tables, right? Yeah, exactly. If we divide that table into multiple tables, the repetition won't happen, and this process is only known as normalization. Okay, we are minimizing the redundancy by dividing a one big table into more sub tables, right? So now let's understand the kinds of normalization. If we talk about the normalization, there are couple of normalization like first normal form, second normal form, third normal form, and Boyce Codd normal form. And there is also fifth normal form, but majorly we go up to third normal form. So we will be focusing on these three normal forms. So what the first normal form is saying? First normal form is saying that each cell should contain a single value and each code should be unique. If you notice this table, we are having multi-valued attributes. If you see the book title, in the same book title, we are having one book. And then again, in the same table, we are having another book. So we are having multi-valued attribute in the same column, right? So this violates the first normal form. Now, how we can fix this? We will create two entries out of this instead of one entry. So what I will do, I will create a one entry for first book and then I will create another entry for second book. This way, in my book title column, I am only having a single value throughout the table. If I talk about how this table will be uniquely identified now, if I just take the order ID, will that be unique based on order ID? No, right? Because we are having one order ID repeating two times. So in this table, we will be having order ID and book ISBN as a primary key. Okay, so we will be using order ID and book ISBN together, and that will become our primary key, which will uniquely identify this table. Once I defined this primary key inside my DDL, this table is gone into first normal form and it is following all the two rules defined in first normal form. Cool. Now let's discuss about second normal form. Second normal form is saying that my table should be in first normal form and it should not be functionally dependent on any subset of the candidate key. So it is only saying that no known key column should depend on any part of the primary key. So there are no partial dependencies allowed on the primary key basis. If you see this table, my primary key is combination of order ID and book ISBN, right?
But if you see this table only, customer name, customer email, and customer address depends only on the order ID. Okay, it is not dependent in any way on this book ISBN, right? This is known as partial dependency, and all these things violates my second normal form. By seeing all of this now, we need to break this table into subtables. Okay, I will create a first table which is orders table, and in this I am having a primary key of order ID, and all the columns are fully dependent on this order ID, right? Now the second table I will create is books, and in this I am having a book ISBN, and all the other columns are fully dependent on this ISBN column. And similar way I will create one more another table which is order items table, where I will define the original primary key, and it will refer the other two tables which we created. And in this way, my tables are now in second normal form as well. Now let's discuss about third normal form. Third normal form should fulfill all the conditions from second normal form, plus it should be having no transitive dependency. This means all the columns should be directly depending on my primary key. Okay, if you see this table, customer email and customer address is dependent on customer name, which is known key attribute, right? This breaks the law of third normal form. Ideally, customer if customer email and customer address should be dependent on my order ID, then it is fine. But here, customer email and customer address are depending on the customer name. Okay, and not on order ID. This violates my third normal form. And in order to fix this, I will again create two tables out of this one table. And I will create a customer table. In this, I will define a new primary key naming customer ID. And in this way, my customer name, customer email, and customer address should be fully dependent on this customer ID, right? And I will define another table as orders. Here I will define the primary key as order ID, and then I will take the customer ID from customer tables, and I will assign the foreign key for customer ID referencing my this customer tables. In this way, there are no transitive dependencies now, and I can say that this table now is fulfilling all the conditions for third normal form. Let's now discuss about the another important concept, that is data modeling. The major purpose of data modeling is it improves the data quality and it aids in understanding the data relationships, and it also facilitates efficient retrieval and analysis of your data. If I go to the definition, data modeling is a process of creating a visual blueprint for information systems, defining how data is stored, structured, and related within a database. Okay, it organizes the complex data, and it also ensures the consistency and translates your business requirement into technical, actionable, and optimized data models. So it and that eventually helps in bridging the gaps between the business and your data. There are three primary data models. Okay, those are relational data models and dimensional data models, and third one is entity relationship model. There are also several other models as well, but they are not in general use, like hierarchical data model, network data model, object oriented data model, and multi-value data model. Okay. In general, the model type defines the logical structure, how data is stored logically, and therefore how it is stored, organized, and retrieved. So if we talk in very general, data modeling is nothing, it's just a concept to structure, organize, and store the data to the related databases. It have primary three data models, that is relational, dimensional, and data model. Okay. If we talk about the relational is although older in approach, but still the most common database model in use today, which stores the data in fixed format records and arranges the data in tables with obviously rows and columns. The most basic type of data model usually have two elements, that are measures and dimensions. And measures are nothing, just a numeric just the numeric values such as quantities and revenues used in mathematical calculations like sum or average. Dimensions can be text or numeric. They are not used in calculations and they usually include descriptions, locations, etc. And in relational models, the raw data is defined as measures and dimensions. Other terminology used in relational database design includes relations, which is just the tables with your rows and columns. And second terminology used is attributes, which we call columns. And then tuples, they are very similar to rows. And then there is a other terminology that is domain, which is just a set of values allowed in the column. Okay, that's pretty much about relational databases. This relational data model, this is very old approach, but this is still in use in many scenarios. Cool. If we talk about the most popular one, that is dimensional data model. Dimensional data model is less rigid and structured. Okay, the dimensional approach favors a contextual data structure that is more related to business use or context. Okay, this database structure is actually very optimized for online queries and data warehousing tools. Okay, and all the critical data elements like transaction quantity, for example, facts, and are accompanied by reference information which are called dimensions. All these things are part of the dimensional data models. Okay, these are optimized for online queries and data warehousing tools, and it usually have facts and dimensions. Okay, third one is data model. So entity-rich data model represents a business data structure in graphical form. Okay, and it contains the boxes of various shapes, representing the functions or entities, and they are, joined together to represent the allocations, dependencies between the tables, and even relationships. So model is then used to create the relational databases with each row representing an entity, and the field in that row contains all these attributes. So it's like it's the key data linkage between the tables. It states how the tables will communicate with each other. That is also very popular one. It is majorly comprises of activities like functions or entities, and each row here represents an entity, and the field in that row contains the attributes. Now we know what are relational data models, what are dimensional data models, what are data models. The whole process of data modeling, generally moves through three stages. If I talk about how these data models work, the whole process of these data modeling actually revolves through three stages. Okay, and if you see in this picture, so I had mentioned these three stages, that is conceptual model, and then logical model, and then physical model. So physical model is last process where we describe and implement all the database, all the data model inside our data warehouse. Okay, if we talk about conceptual model, now it's important to remember that this is the big picture model. Okay, this conceptual model is a very very big picture model, and at this stage we are not getting bogged down into the tiny details of every single data point. Okay, we are not going into very 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 detail here. Instead, we just look at the overall structure of the entire plan. We see that what data we needs to pull, what data is not required. So all these high level information we gather in this conceptual model. So this is almost always our starting point. Okay, we use this conceptual model to identify our main data sets, and more importantly to figure out how the data actually flows, okay, through the organization from point A to point B. This is very important. Okay, this is the main starting point where we have all the high level details, and we understand and figure out how the data will be flowing from A to B. Okay, think of the conceptual model as your very high level blueprint, and you would not start laying bricks without floor plan, right? So this model serves as a foundation, okay, for the more detailed logical model and physical models that will come later. And it's a vital piece of documentation because it keeps everyone on the same page regarding the overall data architecture. Okay, now let's talk about the logical data model. Once we have the big picture vision, okay, from our conceptual model, we move next step into our second level of detail, that is known as logical data model. Okay, when people use the journal term like data model, this is usually what they are actually talking about. They are talking about logical data models. This is where we describe the specific data flow and what the database content is really going to look like. Okay, think of it as a adding the meat to the bones, okay, of the conceptual model we discussed. Okay, now here is the key. The logical model is detailed, okay, but it still technology neutral. Okay, we are not now, even at this point, we are not going very much tech specific. We are not worried yet about whether we are using SQL or Oracle or any specific software. We are just focused on what. Okay, what is this? What is this? Not on how. Okay, this is our detailed view. Okay, this is where we define the specific names for our table, the exact attributes for our entities, and how all these entities will be related to each other. All these things we define in our logical data models. If you are working with the data warehousing, this is also where we map out our facts and dimensions. Basically, it's all the granular information we need before we actually go out and build the things, right? So this is the one place where we have all these things getting ready so that we can actually go the next level to build the systems. Okay, now let's talk about the physical model. Physical model, this is where we actually starts to build the systems. Database specific designs, including your tables, columns, and data types, all are defined and built here. If you ask me which data model we generally use, so data engineers majorly focus on this dimensional data modeling. This is our bread and butter. And let's deep dive into that because that is very important from data engineering point of view. Before I deep dive into dimensional data modeling, I want to take two steps back. Okay, I want to first discuss about the facts and dimensions, and then I want to discuss about the star and snowflake schema. Okay, these two things I want to discuss with you before actually deep diving into dimensional data modeling. Okay, if I talk about facts and dimensions are nothing, are just the fundamental components of data warehousing. These are used to model your the business data, and facts are quantitative and measurable metrics like sales amount or quantity. Okay, and they are stored in the large tables, and whereas dimensions are very descriptive and qualitative context. Okay, like time or consumer name or product name, product category, these column kind of tables will be there in dimensions, so all are stored in smaller tables. Okay, now let's go to the definitions. If I go with the fact definition, it states that fact contains numerical data and foreign keys that links to the dimension tables. Okay, and what is the definition of dimension table? Dimension stores descriptive attributes, okay, which are used to filter, group, and label your data. Where facts contain numerical data, dimensions contain descriptive attributes. Okay, this is the major difference between the facts and dimensions. Okay, second is, if I talk about the characteristics, it contains high volume of data, fewer columns, numerical, additive, semi additive, and non additive data. Okay, facts majorly includes very high volume of rows, but if I talk about the characteristics of dimensions, so dimension have a lower volume of rows, many text based columns, and hierarchical structures. The examples of facts are sales amount, quantity sold, transaction, date, key, etc. And the examples for dimensions will be product name, customer location, date, promotion details, etc. And the types of facts are, there are three major type of facts. Basically, there are four, but major are three. That is transactional, periodic snapshot, and accumulating snapshot fact. The fourth kind of fact is factless fact, and don't worry, we will deep dive into all these kind of facts in next few minutes. And the major types of dimensions are scds, confirmed dimensions, degenerate dimensions, junk dimensions, role playing dimensions, shrunken dimensions, and date dimensions. Okay, so now you understood, right, that facts are usually known for numeric data and foreign key storage, where dimensions are known for descriptive data. In fact, we can have tons of rows, but dimensions have less rows compared to fact tables. And types of the facts you know now, and types of dimensions also you know now, right? Let's begin with the dimension types and understand each and every kind of dimension type one by one, starting with slowly changing dimensions. Okay, slowly changing dimensions are all about how you manage changes to dimensional data over time in your data warehouse or analytic systems. Okay, as the name suggests, so this is the dimension where we manage the changes in the data warehouse over the period of time. Okay, so there are five types of scds. Okay, scd, I am just using a short term scd. So the five types are type 0, type 1, type 2, type 3, and type 4. We will cover up to type 3, and type 4 I won't be covering, as type 4 uses two tables, one for current record and one for historical record, which is nothing but type 1 and type 2 tables. Okay, so if you understood the type 1, type 2, and type 3, you will automatically be very much aware about the type 4. So that's the major reason I will not be covering the type 4. Okay, if I talk about type 0, these are the values that never change. Okay, think of them as the constants in your data attributes that are historically accurate and should not be updated. Examples include a customer date of birth, right? Date of birth can never be changed, right? A product launch date or even a country code. These things never change. Okay, so these are the pretty much examples. If when to use the type 0 is when the data is static in nature and you are not expecting any kind of history, because the data is not supposed to evolve. The example for that type 0 is this table, where here you can see that we are having the date of birth, which is never changing, and if we employee ID as well, which is never going to change, and similarly full name, which generally never changes, right? Now, if I talk about the type 1 is used when data can change. Okay. Type 0 is static. You understood that, right? Type 1 is something where data can change. Okay. This is important to note. But you don't need to keep the old values. Okay. You don't need to actually maintain any kind of history here. Every time a change happens, okay, the old value is overwritten by the new one. Okay, it's very simple, very efficient, and good enough when you only care about the current state of the record. Okay, for if when to use this, when the current accuracy is all that matters, use this for operational data like contact info or profile fields that change but don't need any historical analysis. Like if I talk about the example, if you see this example, the John's phone number was this one, but yesterday he changed his phone number. So in the type 1, what will happen? This record will only get updated to the new phone number. Okay, so we are not maintaining any history, we are just updating the phone number, and we are just letting the system only hold the current state data. This is pretty much about type 1. If I talk about the type 2 and the most famous one, this is type 2 is your go-to tool when you want to track every change to an attribute over time. Okay, this tracks your full history. Okay, instead of overwriting the old values like you had seen in type 1, you insert a new row for each version, okay, keeping a full history of changes. Each version have the same natural key. The natural key will not be changing, okay, but a different surrogate key will be generating, and metadata like timestamps or flags, whichever we will be using to track these versions, will be active for the latest records, okay. When to use this? This is idle for slowly evolving entities like products, employees, where you want to measure how changes affect your KPIs over the time. Okay, if I talk about the example, this is the initial data which I was having, where John's phone number was this. And if you see, I had maintained a column called flag column, and it is saying current flag is yes. This means this record is active. Now, what happened yesterday? He changed his phone number. Okay. Earlier in type 1, when John changed his phone number, we just updated the same record. But now he again changed his phone number. This time we will be doing a new entry. We will be adding the end date, and the current flag we will be updating as no, and the new record current flag will become yes. This is how we actually track our history, and even we have the current status that this is our active record and this is our inactive record. So this is complete versioning of your data, and this is also known as soft deleting the data. Now, if I talk about the type 3 dimensions track changes in a row by adding a new column. Instead of adding a new row with a new surrogate key like with the type 2 dimensions, the surrogate key remains the same and an additional column is appended. Okay, when to use this? Use type 3 when you only need to keep one prior version of a value. You don't need to store your complete history, like just for referencing or comparison. Okay, and this is the example that when in type 1 he changed it, we updated this one. When in type 2 he changed phone number, we added the new record, right? And in type 3, when he changed it, we mentioned a new column called previous phone, and we updated this one here and added the new here. Okay, and we obviously updated the effective date as well, that when this change got effective into our systems. Okay, this is pretty much about type 1, type 2, and type 3. Okay, these are very important and regularly used in your data warehouse, so you will be encountering with them on your regular basis. Okay, so do keep these in mind. Now we had covered the slowly changing dimension. Let's also discuss about the confirmed dimensions. In data warehousing, a confirmed dimension is a dimension that has the same meaning to every fact with which it relates. Okay, confirmed dimension allows facts and measures to be categorized and described in the same way across multiple facts. Okay, see here, guys, dim product is getting used by multiple facts. Okay, so the definition is saying a dimension shared identically across multiple facts. Okay, these kind of dimensions are known as confirmed dimensions. So the same dimension is used by multiple facts across and multiple departments as well. So these kind of dimensions are known as confirmed dimensions. Okay, simply if I put that, a confirmed dimension is something that can be referenced by multiple fact tables in your data warehouse. Okay, next is junk dimension. A junk dimension is a data warehousing technique that groups your miscellaneous low cardinality flags, okay, and indicators, all these miscellaneous columns into a single dimension table. So you can simply say all those junk columns into a single dimension table, which is we will be creating a separate. It prevents the fact table from becoming bloated with numerous small dimension keys, and it actually simplifies your star schema, which eventually leads to improved performance, and it actually keeps your model very clean. Okay, if I talk about the example, this is the initial fact. In this fact, if you see, I am having couple of columns like order ID, date key, total amount, payment method, status, and gift. So what I am doing, I created a junk dimension on top of this fact, and I had moved these three columns into this junk dimension, and I had given the surrogate key, junk key to those columns. And now what I will do is I will tweak my fact, and instead of these three columns, I will only add the junk key which will be referencing to this table. So this is how we can create junk dimension. These are really very helpful, in improving the performance and keeping the model very, very clean. Okay. Now let's discuss about the shrunken dimension. The shrunken dimension is the subset of base dimension that contains only a portion of your original attributes. Okay, it's very straightforward one, and it is most commonly used in data marts where you don't need the full details. Okay, and if I talk about the example, let's suppose this is my original table. Table name is dim product, and it is having couple of columns. So what I will do, I am seeing here redundancy like category and subcategory. What I will do, I will create a shrunken dimension, and I will pull the category and subcategory column into another table, which is known as dim product category. And in the place of these two columns, I will just add my surrogate key. In this way, I had created a shrunken dimension which actually made my model more cleaned. Fourth one is date dimension. A date dimension is the foundational table in your data modeling, which contains one row for every day, and it is used to enable your comprehensive time-based analysis. Suppose year over year growth you want to know. It typically includes attributes such as year, quarter, month, day of week, holiday indicators. Okay, and you can filter and aggregate the data based on these kind of dimensions very effectively. Okay, so if I go to the definition is saying the crucial table storing date related attributes for temporary analysis, that is known as date dimension. If I talk about the example, this is the date dimension looks like. So here you see I am having a date key, I am having the full date, day name, month name, quarter name. So this is a functional table, right? This is a functional table with one row for every day, and it is very useful when you are doing your time based analysis. Okay. Next one is degenerate dimension. Okay. Degenerate dimension is a dimension key. Okay. Such as, let's say, invoice number or order ID or transaction ID. And these are stored directly in the fact table rather than having a separate dimension table. Okay. It is used in Kimball dimension model to group related items without requiring a lookup table. And obviously, it improves the query performance and it reduces the cluttering. If you see this example in this fact table, I had introduced one. I was only having a single column that was transaction number. So I had introduced here. So this is a very good example of degenerate dimension. Okay. It's just adding your dimension key directly in the fact tables. Okay. Next is role playing dimension. Role playing dimension occurs when a single dimension table is referred multiple times in the same fact table for multiple different purposes. Okay. A single table is referencing the same fact table multiple times in a multiple behaviors. Okay, if I quote that, a single physical dimension used multiple times in the schema for different purposes is known as role playing dimension. If I talk about example, if you see this, there is a table called fact sales in which I am having three columns like order date key, ship date key, and delivery date key. And there is another table which is known as dim date, and it is only having the date key, and that same column is renamed in our fact table by multiple names, and it is playing a multiple roles by referencing the same table multiple times, right? So this is a very good example of a role playing dimension where this dim date is acting as a role playing dimension. Now let's talk about the facts. So as we discussed that there are four kind of facts, that are transactional facts, periodic fact, accumulating facts, and factless fact. Let's start from transactional facts. A transactional fact table is the most granular fundamental table in your dimensional data warehouse, recording one row for every single specific business events. Example, each line item on a receipt or your bank deposit. It captures the atomic level data. okay, at a specific point in time, and it enables detailed analysis and high dimensional slicing of your data. So this is the most granular level fact table, and it records every single row inside it. Okay, this is as a definition is saying, it records the lowest level atomic details of an event. Every single record, a customer bought something will go here, a customer cancelled something will go here, a customer ordered something, then cancelled it, then refunded, applied for refund, it will go here. All these single lowest granular level of information will be stored in these kind of facts, and these facts are known as transactional facts. Okay, imagine a customer walks into a store and buy 3 items. In a transactional fact table, this event is recorded with very high precision. As you can see the example, every item will be recorded with very high precision and will go to store every atomic level of details. Okay, this is transactional fact. If I talk about the periodic snapshot fact, these facts store aggregated cumulative performance metrics at regular predetermined intervals rather than individual transactions. So it is very ideal for trend analysis, and these tables represent the state of a business process at a very specific point in time. And it is commonly used for inventory levels, bank balances, and performing the metrics. Okay, if you see this example, in this scenario we don't record every individual deposit or withdrawal. As you can see, we just done for the month level deposit and withdrawal. So this is the very good example of periodic snapshot. Here we are taking the snapshot of the account status at end of every month. Okay, third is accumulating. Okay, accumulating snapshot represents the entire life cycle of a business process. Okay, for example, from order to your delivery, you ordered something on Amazon, and till the time the delivery is not happening and you got the order delivered at your home, till that level, all the life cycle from your order to shipment to in transit to out of delivery to delivery, all these details are the life cycle of a single entity, right? So all these life cycles are stored in this accumulating facts, and it captures multiple milestones and dates. It is updated as the process progress, as I just discussed, that if the process is ordered, it will go ordered, and when the company uh, is accepted your order, it will go to in transit, and same way it will go for out of delivery and then delivered. So it captures whole process, and that actually makes it ideal for tracking the workflow velocity and measuring the times between steps such as order, pack, ship, and deliver. Okay, if I talk about the example, here is a very good example. In e-commerce, an order goes through several stages. Instead of looking at these as separate events, we use one row. As you can see, we are just using the one row to track the entire journey. Okay, if you see the example order 101, we are having only single row where we are having date, ordered, approved, shipped, delivered, total days, and amount. So all these things are managed by a single life cycle. A single row is representing a complete life cycle of a process. Okay, so this is known as accumulating snapshots. Fourth one is factless facts. A factless fact is a database table in a dimensional data warehouse model that records events, relationships, or conditions without containing any numeric measurements. Okay, it is not having any kind of numeric measurements or your metrics. It consists solely of foreign keys from your associated dimension tables, okay, to track the occurrences, let's say about your attendance or your trainings or your product promotions, etc. It is useful for recording the events, relationships, and conditions. That's all about the facts. Now you know the transactional fact, which is a very low level granular fact where we store each and every information. Second, we had understand the periodic fact where we store the aggregated and cumulative data, okay, rather than storing all the individual transactions, correct? Third is accumulating snapshot fact, which actually represents the life cycle of a single row. So it is a journey. Okay, it is a journey for a single row. Fourth is factless fact, in that we are not having any numerical measures and we are only recording the events, relationships, and conditions without containing any kind of numeric measures or metrics. Cool. Now let's discuss about two of the most common database schema types for organizing analytical data, that is star schema and Snowflake schema. What is star schema? A star schema is a way of structuring your data to make it easy to understand and fast to query, especially for reporting and dashboard uses. So at the center, we have a fact table, okay, which contains all the measurable business data like sales, clicks, revenue, inventory changes, etc. Around it, we are having the dimension tables that add the context to each fact, right? So if you see, the dimension tables are not having any kind of sub-dimension table. So these are denormalized, okay, meaning it stores all the descriptive information in one place only instead of defining more subcategories, right? So it is storing all the information in one place, and this makes this kind of schema as star schema. When it's come to performance, it is very, very fast and it is very optimized for reporting and dashboard use case purposes. Okay. Now let's discuss about Snowflake schema. Snowflake schema use the same basic concept as a central fact table connected to dimension table, but but with more structure. Okay, it means we are normalizing the dimensions. Okay, in Snowflake schema, dimensions are normalized, meaning they are broken down into subtables. If you see here, dim customer is further broken down into two more dimension tables: dim customer city, dim customer country, right? Same way, other dimensions are also broken down into other subtables. Okay, so it actually creates a hierarchical model which is very, you know, hard to maintain and it is not optimized for performance, but it still is very useful because it is reducing the redundancy across your data. So Snowflake schema is very best for that. It is known for reducing your redundancy and it normalizes your data. Cool. Let's now discuss about the difference between star and Snowflake schema. So if I talk about the structure, a star schema stores all the related dimensional data into a single denormalized table where product name, category, and brands all sit together. We just seen that. While the Snowflake schema splits the same data across normalized tables. Okay, it divides the data into more sub tables. Like for one for product, we will be having other tables like product category, product brand as sub tables, right? This makes the star schema flatter and easier to query, while the Snowflake schema more accurately reflects the real world hierarchies. Okay, and next is ease to design. A star schema is very easier and faster to design because it avoids any kind of normalization, and you create the fact table with the few dimension table. This is very straightforward. And but while in Snowflake schema, it requires more forethought. Defining hierarchies is very important here. You need to normalize the data, and splitting dimension into subtables is also very important. And also you need to maintain the relationships between those tables as well. So that makes a star schema a good fit for ad hoc reporting, while Snowflake still works better for long term structuring, right? You notice things, right? You notice this, right? Snowflake schema is focused on structuring the things. Okay, so it actually increases the reusability of the tables as well, right? Now let's talk about the query speed. Obviously, star schema often run faster because we are having fewer joins to make. Okay, and it is a big win for your large data sets, while the Snowflake schema introduce more joins as we are having more hierarchical tables. So more joins, more normalized tables, more joins, we know that. So which actually slows down the performance unless it is very well optimized. Okay, that said, There is another out of context point. Nowadays, even cloud data warehouses are very intelligent, and they are having a very intelligent query plannings like Snowflake and BigQuery have. And anyway, this performance gap is narrowing down now, but it will still take a couple of years to really narrow down to the level of star schema, but it's work in progress from many big companies. Fourth is storage. A star schema duplicates data, obviously, because we are storing all the information in a single table, and we are repeating multiple rows here. So it will obviously take the more storage, okay, because we are having duplicate data in the same table. But in Snowflake schema stores the unique value only once, because we are reducing the duplication and actually saving the space, okay. That actually translates to lower cost in cloud environment where storage also adds up, right? So this is the perk in favor of Snowflake schema. If I talk about updates, so a star schema can make updates painful. Changing a category name might mean updating thousands of rows because we are having duplicate data. So updating star schema is very, very painful, guys. Okay. But when it's come to Snowflake schema, you just need to update a single entity in the related dimensional table and you are done. So that is something which is very, very efficient when it's come to updating the data. Okay. And last point is debugging. A star schema can obscure the data lineage since values are obviously packed into a single table. So debugging is not going to be an easy task here. But in Snowflake schema, it keeps the relationships very clear, and that makes it easier to track issues or audit the data. Okay. This clarity is crucial in industries with the strict compliance or data governance needs, as you know, right? So this is the pretty much about star schema and Snowflake schema. There are pros and cons for each and every of these things, but majorly star schema is denormalized and Snowflake schema is normalized. When it's come to performance, star schema will give better performance and Snowflake schema will lag. But now this gap is also narrowing out. This is still out of context, but you should know that this process is also going on. Okay. Storage, star schema will be more costlier compared to Snowflake schema. Okay. And update is really very painful in star schema, guys. Really very painful. Okay. But in Snowflake schema, it is very, very easy. Just go to the related table and update it on the one entry and you are done and dusted. Okay. That's pretty much about star and Snowflake schema. Let's now discuss about dimensional data modeling. Dimensional data modeling is a Kimball designed technique for organizing data warehouse information into facts and dimensions. We just covered it, right? Optimized for high performance retrieval and user friendly querying by using star or Snowflake schema. So, dimensional data modeling is nothing just to organize your data in the data warehouse in the form of facts and dimensions. Cool. There is a four-step design process involved. First is selecting the business process. Second is declaring the grain for all these individual items. And then we need to identify the dimensions we need to create. And then we need to identify the facts and the kind of facts which is required for the business. There are a couple of benefits and use case for this dimensional data modeling. First is it supports fast querying. It is designed to minimize joins and maximize your analytical speed. When it's come to ease of use, it is intuitive for you end users to understand and browse the data. When it comes to consistency, Conformed Dimensions ensure consistent reporting across different business processes, and the common applications involve data warehousing, business intelligence reporting, and OLAP systems. Cool. Let's discuss about very interesting topic, that is data vault. Think of it as data vault is like a set of super smart building blocks designed specifically for holding your data. Okay. And these blocks are not just for building any old structure. They help you create an organized, easy to understand, and super flexible data that can grow and change as much as you need it. Okay, it is completely super flexible way to create, organize, and store your data. If I go to the definition, data vault is a agile, scalable model method for enterprise data warehouse designed to handle large scale historical data integration from multiple sources. It uses a hub and spoke structure. Okay, this structure have three core components. That those are hubs, links, and satellites. We will come into that one by one in 1 minute or so. To separate business key from descriptive context, okay, allowing for easy incremental updates without disrupting your existing data structure. So this is really cool. It is a very flexible way to have your data structured. Okay, it consists of three core components, and as you just listened that it uses a hub and spoke structure, which obviously consists of three core components. The first one is hub. Think of a hub as the main landmark for your data city. It's the central point for everything related to a specific business concepts. Imagine we have a hub for customer. Okay, this hub only stores the unique ID. Okay, it don't store anything else than unique IDs, maybe their names. Okay, it's like the city hall for your customer data. Okay, so as the definition say, hubs are only used to store the unique business keys. Okay, and next one we have links. Links are like roads and bridges connecting all the different hubs together. Okay. If we have a hub for customer and we have another hub for product, okay, a link block would connect them to show that a specific customer bought a specific product, right? It is a connection between multiple hubs. Okay. It's like a highway connecting the customer to the product warehouse. Cool. Lastly, we have satellites. Satellites are like the buildings that hold all the detailed information. Imagine customer hall has many floors. Okay. Each floor represents a different satellite. One satellite might hold the customer address, and even another might store their contact information or other information, and another might track even their preferences. So, this is hub, links, and satellites, where hubs are used to store the business keys. Links are used to represent the relationships between the multiple hubs, and satellites store the descriptive time variant information about all the hubs and links. If I talk about the key benefits, the biggest benefit for Data Vault is scalability. It is very efficient to manage even petabytes of data because we just need to create the hub, link, and satellite, and we just connect the dots, and our work is done. It is very flexible as self-explanatory because we can easily adapt all the business requirements and even the new requirements very easily. It is very good for auditability. It provides a complete historical, immutable records of data, and it is really a good example of automation. Now let's discuss about data lakehouse. To understand the lakehouse, we first have to look at its parents. Okay. First, we have a data warehouse, right? Think of this as a high-end organized kitchen. Everything is cleaned, chopped, and put in labeled jars before it enters. Okay, it's great for business reports, and it's expensive, and it cannot handle raw ingredients like unformatted images or videos. We had also pretty much covered data warehouse a lot, and I assume you know a lot about data warehouse. You know what I am talking here. Okay, then we have data lake. This is also very interesting. A giant shipping warehouse. You can dump anything in there, even raw data, logs, or sensor clips. For it's very cheap. Okay, it's great for data scientists who want to explore, but it often becomes a data swap because it's messy and it's hard to search and lacks the rules that keep data high quality, right? third one is data lakehouse. This is exactly what it sounds like. It's the best of both the worlds. Okay. It takes the cheap, flexible storage of data lake and adds the structure and speed of data warehouse right on top of it. Okay, so it's optimized and best of both the worlds, either of data warehouse and data lake. It uses a special metadata layer. Think of this as a super smart librarian who stands in the middle of that giant shipping warehouse. Even though the data is stored cheaply in its raw form, this librarian keeps a catalog. Okay, it keeps a catalog for everything. This ensure that the data is clean, follow strict ACID rules, and allow you to run fast searches just like you are running these searches on your data warehouse. This is a data lake house architecture, and here we are having structured, semi-structured, and unstructured data, which we are loading either by batch or stream processing into our data lake. And on top of that, we are having a catalog or metadata layer, which is storing all the metadata related information. And this data now is directly usable by BI reporting and data science or even machine learning. So this is a data lake house architecture. So if I go to the definition of data lake house, it is the definition is saying data lake house is a modern unified architecture that combines the cost effective flexible storage of data lake with the data management, asset transactions, and schema support of data warehouse. It enables storing, managing, and analyzing structured, semi-structured, and unstructured data on a single platform for AI, BI, and data science. Okay, this is all about data lake house. It is best of both data warehouse and data lake. Okay, it's combined all the best features of data warehouse and all the best features of data lake into a single platform. Let's talk about key characteristics and benefits. It's the unified architecture, and we already discussed that it combines the low cost object storage like your S3 or ADLS storage with structured management, and it enables ACID transactions on these data lake storage directly, and it uses open formats such as Parquet, HUDI, and Delta Lake, and it allows direct access from various engines. So performance and scalability, it supports high performance SQL queries for BI as well as AI ML workloads on a single scalable repository. It is often implemented using Medallion architecture to refine the data for analytical use. Now, if I compare the lake house and data lake and data warehouse very quickly, I know you understood that, but let's just get the complete gist about the comparison. So if I talk about data warehouse is highly structured and performant for BI, but expensive and poor at handling unstructured data. Data lake stores vast amount of raw data, either it's structured or unstructured, but it can become unmanaged and it actually lacks the ACID guarantee. So if you had stored your data in S3 in the raw form, either is structured or unstructured, so it is a very much tedious task to manage the ACID properties and manage the metadata. Although you have Amazon Athena to do that kind of to query the data from the SQL, but there are still limitations. But when it comes to data lakehouse, it bridges these by adding a metadata layer on top of the data lake, and it offers PI performance on your raw flexible storage only. So it is best of two. Now let's talk about very important topic, and this topic is something which is non-negotiable in the data warehousing world. This is known as referential integrity and constraint. So have you ever tried to sign up for a website and it didn't let you leave the email field black like like you are seeing here? Or maybe you had tried to delete an account, but it said error, active orders found something. This is not a glitch, guys. This is referential integrity and database constraints at work. Okay, now I am going to show you why these rules are the only thing keeping your accounts, your Amazon orders, or your social media from collapsing into total chaos. Okay, Let's talk about constraints. What are constraints? Think of constraints as the bumpers in a bowling alley. Okay. These are rules we put on a specific column in a table to make sure only good data gets in. If I go to the definition, so SQL constraints are rules used to manage the data in table, ensuring accuracy, reliability, and integrity. They can be applied during table creation or added later using alter table statement, right? So these are the rules which we put on specific columns to make sure only good data flows into our systems. Okay. So if I talk about the some of the constraints, there are like constraints like null constraint, not null constraint, primary key constraint, default constraint, foreign key constraint, unique constraint, index constraint. These are really very important when you are creating the DDL. You should ensure that you are applying the accurate and relatable constraints in the columns. Now, referential integrity is a bit more specific than constraints. Okay, it's the rule that governs the relationship between two tables. Okay, using something called foreign key. Okay, referential integrity ensures two things. Okay, first is no ghost orders. You can't create a order for let's say customer. If customer does not exist in the system, you cannot create the order for that customer, right? Second is no orphaning, like you even cannot delete the customer if he is having some object associated to it. Okay, it keeps the links between your data from breaking. If a parent disappears, the child should not be left floating in the space, right? So that ensures that there are no ghost orders or there is no orphaning happening. Okay. So I will come to the example, but let's first go through the definition of referential integrity. Referential integrity is a database principle ensuring that relationships between the tables remain consistent, valid, and accurate, requiring foreign keys to match existing primary keys. Okay, it prevents the broken links. This is the conclusion of referential integrity. It prevents the broken links such as orphaned record by enforcing rules that restrict how data can be inserted, updated, or deleted across the related tables. Okay, let's take one example. Okay, and let's assume there are two tables. First is customer table, which is the parent table. Second is the orders table, which is the child table. Okay, these are the records present in both the tables. So as the referential integrity definition is saying that referential integrity is a set of active rules that database enforced during data modification. Let's see three scenarios. Okay, scenario one is preventing the ghost orders. Okay, imagine a new record is received for a customer that does not exist. Okay, see here, the customer ID is 99, but 99 customer ID is not present in our parent customer table, right? So if we try to add this row to our orders table, what do you think what will happen? Firstly, the system checks the customer table for customer ID 99, and it is saying that there is no ID of 99, only 101, 102, and 103 exist. So what will happen? The database will reject the insert. Okay, and throw an error. This scenario ensures that ghost orders for a non-existent customer is never going to be created. Now let's discuss about the second scenario, which is preventing orphaning. So Alice Green wants to close her account. Okay, so we try to delete her account from the customers table. The system is looking at 101. System is able to see 101 into my customer table. So system said okay, I got 101. Now system will go into the orders table and it will see there is 101 there as well. So once it sees the 101 into orders table, database will immediately reject the delete request because customer ID which we are going to delete is already present in our orders table. So it will immediately give me error and it will reject the request for deleting my record. Okay, this is the second scenario where it is preventing the orphaning. Okay, Third is the valid scenario where we will see the successful delete. Suppose Charlie has 0 orders, okay, and he wants to close his account. Okay, now let's try to delete this row. What will happen? First, it will see 103 and it will go to my customer table, and it is able to see 103 record. Now it will go to orders table, and when it try to see in orders table, it will not find the 103. So this means the associated link does not exist in the orders table, and as the 0 records are found in the order table, the database will allow the deletion and the relationship is successfully served because there is no integrity rules were broken during the process.
Let's now discuss about some really important terminologies like full load, incremental load, idempotency. If I talk about full load is a data integration process where the entire target dataset is truncated and reloaded the complete dataset again into the system. It is primarily useful for your initial data population where you are actually going to feed all the historical data into the table, and it is also referred as a total data refresh, and it is required to ensure the data integrity. Full load is also referred as initial load, truncate and reload, one time load, day zero load, or full refresh. These are all the synonyms for full load. So multiple times multiple people refer full load in multiple by multiple names, like some say day zero load, some even say do the full refresh, some calls it only OTL. So there are multiple names for full load, so you should know these are many very popular names by which full load is getting referred as. Now let's talk about incremental load. Incremental load is a process where we update our target table by loading only the data which is changed from the last load. We are not loading the complete data like we had done in full load. Here we are only loading the certain amount of data which is only changed or newly came into our source systems. This process is very great as it saves the time and resources compared to full load, and it makes the systems ideal for large data sets, but it requires little bit more complex change detection and management of lineage. As you know, whenever we are doing incremental load, we need to track the time from last ran from the, so that we can start the incremental load from that time to current time. Third is idempotency. Idempotency ensures that all the ETL pipelines, whichever you are running, even multiple times or single time, does not break the rules of feeding the duplicate data into your target systems. So it ensures that all the systems are consistent and it prevents duplicating data. It is very critical for reliability. It allows all these automatic retries even in the scenario when your ETL process got failed. It allows for automatic retries and it reduces the overhead for manual cleanups. Okay. The key techniques we use for idempotency is either merge scripts, or either we delete or replace the partition data, or either we track the state with high watermark timestamps. This is pretty much about full load, incremental load, and idempotency. Full load is a complete refresh where we are truncating and reloading the complete set of data again into our system, and incremental load is something where we load the data which is only changed since the last ran time. Let's talk about the storage format. Storage formats plays a very important role, as these are the ways how your data will be stored inside the systems. If I talk about Avro, Apache Avro is a data serialization framework. It is developed as a part of Apache Hadoop project. It is very efficient and it provides compact and schema based serialization that makes it ideal for scenarios like data exchange, streaming, and even data storage. Avro supports several features that make it a popular choice for big data systems, especially when you are working with Hadoop, Kafka, or any other distributed data platform. Okay.
If I go to the definition, as I just discussed, that it provides the efficient, compact, and schema-based serialization, which makes the Avro formats very ideal for data exchanging and streaming. Same way, definition is Avro is a row-oriented data serialization framework developed within the Hadoop ecosystem. Okay, designed for data serialization, data interchange, schema based, and compactness. If I talk about data serialization, there are two terms basically very relevant to serialization. Those are serialization and deserialization. So, serialization is a process of converting a live in memory objects into a persistent format like bytes or JSON or XML for storage and transmission over a network. If you see, guys, here we are converting a object into a persistent format, either bytes, JSON, or XML, for storing over a network, right? And deserialization is the reverse. As you can see, we are reconstructing that data back into functional objects. Okay, these processes are critical for data persistence, catching the data and communicating between the systems, right? So serialization is process of converting object into format, and deserialization is reconstructing that format into object. Okay, so these are reverse of each other. Now if I come back to this data serialization, Avro can convert structured data into compact binary data format, as we had just discussed here, that streams of byte which is showing here. It can convert into any compact binary format that can be transmitted or stored. Okay, if I talk about data interchange, Avro can be used to exchange structured data between programs written in different languages. You can exchange your programs with any language like Java, C++. When it comes to schema based, Avro format is strongly typed and structured by a schema, which ensures the compatibility and efficiency throughout the process. Okay. And fourth is compactness. Avro is known for compact data serialization, okay, which reduces the storage and transmission. To be very fair, Avro is often used in distributed systems like Kafka, Apache Flink, Apache Hive, and HDFS because of its compact and fast serialization capabilities. Okay, if I talk about the key features of Avro, first key feature of Avro is it is schema driven. Every Avro data file contains metadata about the data structure. If you see here, so it is written that we are having metadata for all the files. It enables cross language data exchange. Second is compact. As we had already discussed, that data here is stored in binary format, which is both smaller in size and faster to serialize and deserialize compared to the textual formats like JSON or XML. Okay, this is language neutral. This is also, we had discussed that Avro supports multiple programming language such as Java, Python, C++, and more. Fourth is splittable and compressible. Avro files are splittable, allowing parallel processing in big data like Hadoop. Avro files can be compressed using codecs like Snappy or Deflate and anything like that. Okay. Fifth is data evolution. Avro supports schema evolution. It is really the coolest feature of Avro that it supports schema evolution that actually allows changes to schema without even breaking the compatibility with any kind of existing data. So suppose you are adding or removing any fields, it will track those changes and it will ensure that these changes are not breaking the compatibility with all the existing data you are having in your systems. Okay, that's pretty much about Avro. Next is Parquet. Parquet is a very popular columnar based file storage, and I assume you had heard about Parquet a lot. This is one of the favorite storage technique when it comes to OLAP systems. Here all the data is stored in the column format, which enables efficient compression and allows query engines to skip any kind of irrelevant data, which eventually reduce the input output cost. This is how the columnar based storage looks like. This is the example of columnar storage. Like earlier, the data was in the row storage, and now we organize the data into column storage by separating the ID, name, and phone number. Okay, and it makes my retrieval process very fast. This is one of the key feature about Parquet. Second key feature is high compression. Columnar data types allow for better encoding and compression algorithms, reducing storage cost by 60 to 70% compared to CSVs. Okay. Third is metadata and performance. Files contain embedded metadata with statics like min or max values, enabling predicate pushdown to skip unnecessary data blocks. We don't need to scan all the data blocks because we have all the metadata and statistics stored. Fourth is schema evolution. It supports flexible schema updates, allowing columns to be added or modified without rewriting the entire data set. Okay. Fifth is interoperability. It is language agnostic, supported across Apache Hadoop ecosystem and modern data lakehouse architectures like Delta Lake and Apache Iceberg. Let's now discuss about the big three table formats. Those are Delta Lake, Apache Iceberg, and Apache HUDI. If I talk about Delta Lake is an open source storage format that brings ACID transactions, scalable metadata, and time travel to cloud data lakes, enabling high performance, reliable lakehouse architecture. It sits on top of existing source storage like S3, ADLS, GCS, and improves upon Parquet with transactional log, facilitating unified batch and streaming data pipelines. It was originally created by Databricks. If I talk about key feature, it uses a transaction log to keep track of every change. Okay, it is best for the teams that already in the Spark or Databricks ecosystem, and it brought all the asset transaction to the data lake, which allows you to update or delete in the Parquet files very safely. If I talk about Iceberg tables, Apache Iceberg is an open source, high performance table format for huge analytical data sets designed to bring SQL like reliability and ACID transactions to data lake. It allows multiple engines like Spark or Flink or Trino, Presto to safely work with the same data simultaneously. Key features include full schema evolution, hidden partitioning, and time travel queries. If I talk about the origins of Iceberg table, these was developed by Netflix originally. Now, if I talk about key features, it uses hidden partitioning where you don't have to tell the engine how to find the data. Iceberg tracks exactly which files contain which data points using the manifest files. Okay, it is best for high performance queries and huge data sets where partition evolution is needed. Next one is Apache HUDI. Apache HUDI is an open source data lakehouse platform designed to bring database like functionality such as ACID transactions, insert and delete directly to cloud and distributed data lakes. As you had seen this thing that all these big three supports ACID transactions, upserts and delete, right? So this make these three very beneficial for cloud data warehouses, and that's the only reason these are very extensively used to store your data. This is the architecture of Apache HUDI. Functionality it is having is ACID transactions, which ensures data integrity for concurrent reads and writes, similar to your traditional relational database. And the second is incremental pipelines. It enables incremental ETL pipelines that only process new or updated data, which drastically reduce the latency compared to your traditional batch processings. Third is managed table services. It automates background tasks like compaction, clustering, and cleaning up old data versions. Fourth is multimodal index. It uses pluggable indexing mechanism like Bloom filters or HBase to locate records quickly for faster updates and deletes. If I talk about the origins of Apache HUDI, the Apache HUDI was initially developed by Uber. And the key feature here is upserts. It is designed specifically for real-time data ingestion. It is best for the use cases with frequent changes to existing data. HUDI is the master of incremental processing, meaning it only processes the data that has changed since the last run. Now, next topic is change data capture. Change data capture refers to the process of tracking all the changes in data sources such as databases and data warehouses so they can be captured in the destination systems. Okay. Before CDC, we used bulk loading. This means every night, let's say at 2 a.m. or based on the schedule, the system would grab everything from the source database, millions of rows, and dump it into your data warehouse. The problem is it is very slow, it's heavy, and if you have billions of rows but only hundreds changed, you are wasting 99% of energy moving data you already have in your target data warehouse. Okay, here comes the CDC to help. It's like a security camera that only records when something moves. Instead of scanning the whole table, CDC watches the database logs. Every time a row is either inserted or updated or deleted, the database makes a tiny note in its logbook. This is the logbook. It will make the note here that what's happened in our source, and then CDC will read this notebook in real time and say, hey, this customer just changed his address. Okay, so it will send only the update to the data warehouse instead of sending all the data right now. Okay, usually CDC detects changes in data using three methods. Those are timestamp based, trigger based, and log based. Let's talk about all these three one by one. First is timestamp based. It captures the most recent changes by using columns such as last modified or last updated. Any downstream applications or systems can query these kind of audit fields and get the record that have been updated since the last execution time. Let's see this with an example. This is my source table and it is newly created with two records, and now I have defined my target table which is empty, and as this source data will be flowing first time into my target table, I had stored my timestamp as 1900, which is way back than my last modified time here. So what will happen when I will go with the timestamp based CDC? It, for the first time, it will see that the stored date is always less than these dates. These dates are eligible for processing into our target table. So it will process these two records into my target data warehouse successfully. Okay. The second scenario is now next day in the source table, the new record came. Okay. And now what will happen? On the second day, it won't start from this 1900 to look into last modified and process it. It will store the latest date from the previous run, which is this one. So it stores that date, and this time it will trigger from this date onwards. So second run or next time run, it will trigger from this dates onward, which eventually will only populate single record in my data warehouse instead of populating all the three records. There are pros and cons for every process, and same for time based as well. We have couple of pros and cons for this approach. The first pro is it is simple to use and implement, as we are just storing the date and based on that date we are extracting the data, and it provides a straightforward way to track changes over time, as you had just seen this, right? The biggest con is it can only process soft delete, not the delete operation. Suppose you had deleted something here completely. Okay, it won't be tracking that, right? There is no way that it will track because you are only storing the date. You are not storing the complete record. Okay. It adds the computational overhead to the source system because the target system have to scan each row in the table to identify the last updated value. Okay, and it requires changes to the existing database schema sometimes. Next one is trigger based. The most database uses trigger functions. These are store procedures that are automatically executed once a specific event such as insert, update, or delete a record occurs on your table. One trigger for each operation per table is needed to capture any kind of data changes. These changes are stored in a separate table, commonly referred as a shadow table, as you can see here. So this is the shadow table where we are only tracking the changes. Additionally, developer can include messaging systems so that these data changes can be published to the queues where relevant targets subscribe to them. If you see this diagram, in my source system, these three operations happened. For customer 101, the new record came. So the operation in my shadow table go on insert, and I deleted the customer 127 from my actual source table. Due to that, it is showing that 127 got deleted, and I updated the address for customer 142 in my source table, and it is showing that customer 142 is updated. So this is my shadow table. Now I will use the shadow table to populate data into my final target table. Okay, so I will see the operation is deleted. I will delete the record. I will see the new record is inserted. I will insert it. And if there is any update like email or phone number, I will update it. This is how the trigger based CDC works. Okay. Obviously, here also we have couple of pros and cons. And the pros here is that we can detect and capture all the type of changes to the records, and the triggers are widely used and are supported by majority of the databases, and it enables real time data capture without pulling anything out. Okay. And the cons are it negatively impacts your source database performance since updating records require multiple writes into your shadow table. It requires changes to be to the source database schema, and it can become complex to manage with a large number of triggers, right? Suppose you are having tons of trigger, it will be complex for your system to manage all these triggers, right? Third one is log based. Transactional databases log all the changes like inserts, updates, and deletes committed against the database and their corresponding timestamps into files called transaction logs. This is the difference. Okay. Here we are maintaining the transactional logs to store all these information instead of storing in a table earlier in the trigger based, which we did. Now we are storing the changes in the transactional logs. Okay, and these logs are primarily used for backup and disaster recovery purposes, but they can also be used to propagate changes to target systems. Data changes are captured here in near real time. Since target system can read from transaction logs, this method does not impose any computational overhead on your source database. That's the biggest pro for this log based CDC. So you are changing something in your source, and that change is flowing into your transactional log, and using the log miner you are detecting the latest logs and populating and updating your target database respectively. It reduces the overhead on your source database, and all these things are tracked in your transactional logs. If I talk about the pros and cons here, the biggest pros are it does not add computational overhead. Second is it can detect and capture all type of changes to the records. And third is there is no need to change the schema of the source databases. And if I talk about cons, there is not standardization around the format of transactional logs. This means that each vendor opts to implement their own method, which could change in future releases. Okay. And second con is target systems have to identify and eliminate any changes that were written to the source database but then rolled back. So if you are rolling back something, it become a con in the log based CDC. Cool. Let's now create a dimensional data model based on hospital data. So I had written the requirement here, as you can see on your screen. So this is the complete scenario, and I had divided this scenario into four phases. As you know, usually in hospitals, a patient arrives and go for a checkup with a doctor. For some patients, problems are very serious. For those patients, doctor advise them to get admitted in the hospital, and for some patients they can just pay and go home. Similarly, someone who is admitted In phase 2, they obviously will be requiring some lab test or some kind of surgeries during their time their admission in the hospital. And those facts and dimensions we will be creating. And in phase 3, that patient also requires some kind of medicines, and we also need to store the bed occupancies, how many beds we have and how many beds are occupied. All those details we will be storing in phase 3. And in phase 4, we will be generating the bill, and we will be checking if the patient is going to pay the bill, or if he is having some kind of insurance, so that he can claim insurance and insurance company will be paying the bill. So this complete scenario, we are going to model it based on facts and dimensions. For that, I will use my favorite tool, that is DB diagram. There are other tools also, that is draw.io. You can use whatever tool you want to build this model, but this is my personal favorite as it gives me the flexibility to write the DBML language code myself. So this is very convenient to me, but you can use any other tool. So now, as per phase 1, initially the patient will visit the hospital, right? So I will first create a fact table that will store all these visit measures. Okay. So I will say table fact visits, and what will be the attribute? First, obviously, the attribute will be visit fact key. That is going to be my primary key. Okay. And I will say here it's my primary key. Okay. And as the patient is coming, so I also want the patient key to be generated. So I will define the patient key, and it's integer. This one is my primary key, so this is fine. So it will be my surrogate primary key. But this one is the patient key, and that will be coming from the patient table. So I will also create one dimension table, that is patients, dim patient. Here I will be having that patient key, which obviously in this case will be my primary key. Cool. There will be other attributes also in the in the patient, like patient ID, first name, last name, and then maybe gender, and maybe age, or let's say its date of birth. And here I will say date, and then maybe blood group. A lot of columns, right? So I won't be writing all the columns, but you understood that there are a lot of columns in this patient table, right? So I will just say other columns as well. Okay, so this is my dimension of patient, in which I am having my patient key, patient ID, and all the columns which are related to the patient. So obviously, when patient arrives in the hospital, the staff will ask that patient to fill out a form. In that form, he will fill some details like these: patient ID, patient, or let's say one more like phone number. Okay, so he will fill some details. This table I am going to create as type 2 table, because there is a high possibility that they can admit and they can go home, and then again they get some other illness and they again got admitted into my hospital, right? So I need to track the history. So what I am going to do, I will create this as ST type 2 table. For that, I will be mentioning some audit columns like effective date, and it will be date. And then I will be mentioning other columns like expiry date, flag column, if he currently is in the hospital or not. So I had mentioned the audit columns, and plus other columns as well will be here. So this is my dim patient, which is type 2 table. As I told, that patients can revisit and they can readmit themselves. So this is important that I create this type 2 table. Now I have patient key, fact, surrogate key. What else I need in the visit? So patient came in my hospital and he filled the form, and when he filled the form, dim patient came into picture. Now once he had filled the form, he will go to doctor, right? if we go to doctor, obviously doctor should also be having some key, some ID, employee ID or something, right? So I will mention the doctor key, and obviously as I had mentioned the doctor key, I need to create the doctor dimension as well. So let's create that dimension. I will say table doctor, and then I will mention my doctor key, which is integer, and obviously my primary key. So now this key is also defined, and there will be other details of doctor as well, right? Like doctor ID, which is again integer, let's say, and then we will be having doctor name. This is also very important to record that. And then what else? Maybe gender, specialty of that doctor, right? That is also a good thing to record. Let's record that specialty of that doctor. And then maybe how many years of experience he is carrying. That is also something which we can record. And there are other columns also which we can record. Okay, like his phone number or his active flag, is the doctor is today present or absent, right? So we can record those as well here. That pretty much, I guess. Now I had created the doctor table and dim patient table. That patient is going to visit a doctor, but which doctor he needs to visit, in which department he needs to go, that information is still missing, right? So obviously first I need to define this information in the doctor table so that he can only go to that department doctor. There is a possibility, like if a doctor name is Sham in department A, there is also a scenario where the same Sham other doctor will also be there in department B, right? So we don't want to confuse our patient. So obviously we need to define a department key, which obviously will be integer. And as I had defined the department key, I need to define the departments. So if I define the department here, I will just create redundant entries here if I added the department name and other details, because there is a possibility that a single doctor may be working in multiple departments, right? That is also possible. So instead of defining all these department details in the doctor table, why don't we create a separate department table, right? I know it, we are normalizing this table, but it is important, right? Because I don't personally want a lot of redundant entries for doctor. So I am going to create it. So if you notice something, we are creating the table, but we are not having the links, right? So let's also define the link. In order to define the link, we just do here a reference and then this, and then for patient, this is a patient. So I will say patients dot patient ID. I will just copy it from here. Patient dot patient key. Now it should be creating the, see here guys, it created the link. Same way I will create the link for doctor as well. So I will just say dim doctor, and here I will say dim patient SCD2. Okay, so that you understand clearly. And now I will also create the reference key. I will just copy paste, and then I will say doctor please come here, and then the doctor key also will come. Oops, doctor key will also come here. Perfect, this is also defined relation. Now I had linked my doctor table and I had also linked my patient table. I will just came here. Now I was discussing about department, right? So we had defined the department key, and I want to normalize this table, so I will also mention this thing here. Oops, I will also mention this thing here, and I will create another table which is department table. I really don't want any mess here, so I will say dim department, and then I will copy this and paste it here. And now I need to create the department table. So first here I will, okay, I will create a department table, department, and then here I will mention department key, and then I need other details of department like department ID, which is varchar, and then I will mention department name, right? That is also important. Varchar, and then what else? What else? What else? Maybe floor where this department is located, and I will say integer, and maybe building number if a hospital is having multiple buildings, maybe. Okay, a lot of columns. I will just say other columns here. Okay, you can think about those columns. I am not going to completely describe all these things. You understood what I am saying, so I'm not. So what I had done is I had normalized the doctor table and I had created another department table so that I can reduce this redundancy. So if you see here, this link is also established and it is referring into my department table using my department key. So I have couple of things. So obviously I need that department key here also, right? Because that patient is going to visit that department and I need to know that information as well. So I will just copy paste, and then I will place it here and done. Okay, now what else patient can do? Think about that. Patient came, he filled the form, he that created dim patient table, then the staff advised that patient to visit the doctor in the specific department and he gone to the doctor. Okay, now he had gone to the doctor and he had shown his record to the doctor. Also we need to create a date key because we understood that patient came and he visited the doctor in the specific department, but on what date, that we hadn't captured, right? Okay, let's capture that as well. Then I will create a date key integer, and I will again create a new date table and I will just copy paste this and I will say dim date, and here I will say date key. Perfect, Jaswinder, perfect. Now I have one more task to create a date dimension. Let's create the date dimension then. Dim date, and then I will mention the date key as usual. And it is my primary key, guys. Integer. I personally enjoy this dimensional modeling. This is really cool, right? So now I had mentioned the date key. What else information I need to store in date dimension? And by the way, you know date dimension, right? We had discussed in a complete data warehousing multiple times. This is a role playing dimension. Okay, I will show you today how this dimension will play multiple roles. Okay, let's define a couple of columns for the date for this date dimension. Let's say date key is there. Now let's say full date. I want to know the accurate date when this patient visit, and then obviously this, and then what else, then day of the visit. I also want to capture this, maybe anything between, let's say, 1 to 31, first of May or 2nd of May, whatever the day. And then month also is very important to store, which month, first month, second month, or third month. Then month name, let's store that as well. Month name, let's say varchar. Okay, now I have month name. What else is in the quarter? Quarter is also important. Quarter, varchar, and then year. Very, very important. Although we can extract the year from full date, but I want to capture this. I personally want to capture this year. Okay. What else? Week number. And then what else? Is weekend. Yeah. Because usually on weekends, hospitals get more visits. So Boolean, I guess that's pretty much about the dim table. I had defined the dim table, and why this error? Why? Okay, maybe I just need to copy paste. Perfect, perfect. Now I have my date dimension here. What else a patient needs? He came, gone to the staff, okay, and then staff told him to visit this doctor in this department. We had stored that information, and we know the date when the patient visit, and maybe we can also store location, right? Why I'm thinking about location is, suppose this hospital is a multinational hospital, and there are a lot of branches of this hospital, and every city have a branch for this hospital. Let's assume it's a Fortis or a big hospital. In this case, I also want to know, right, that this patient visited which location, right? In that way I can know that, okay, this patient visited Indore's hospital, this patient visited Amritsar hospital. I want to capture that. Okay, let's capture that. I will say location key. Okay, and obviously it will again be integer. Oops. Integer, and I need to create this table again. No problem, I will create it, but I will just copy paste whatever I can from here, and then I will save this table as dim locations, and I will just copy paste this key here and paste it here. Cool. Now I have another task to create this, and let's create this quickly. Dim locations, and here I will first copy paste my location key, which is going to be my primary key, PK. What else I need in location? What guys you think? What else is needing? Obviously, I need hospital name, right? That's the main reason I created this table, right? I need to know hospital name, hospital branch name, right? Where care, and although hospital name doesn't make sense if you we are just looking at a chain of the same hospital, but I just captured it, so maybe you can skip that. We have branch name, then obviously city in which my hospital is there, which city, and then state, obviously. And what else I can store? Country. Country is also a good column to store. Maybe it's an international hospital. Right? Then maybe region, right? This is possible in a single city. I am having multiple hospitals. Okay, that's pretty much about locations. I don't think there is much needed in location. So I had stored locations as well. Okay. Now what else I can store in my fact? Think, guys, think. I have my patient. I got patient is gone to doctor, visited the department. We know the date when patient visited the doctor. We know the location, that which hospital the patient visited the doctor. Now he visited the doctor, and we also need to count the visits, right? Right. So I will be creating a matrix here, which will be a visit count. There is a possibility that same patient will visit multiple times, isn't it? So I will say visit count. So I am counting the visits. Okay, that's the matrix I created. Okay. Then what else? Okay, suppose the patient visited the hospital and the doctor asked him to go for a lab check. If a person is going for a lab check, I also need to record what diagnosis doctor had recommended, right? So let's create another key, diagnosis key, and I will say this integer, and I need to again create one more table, which is my diagnosis table now. No problem, I will create it quickly and copy paste. Here I will say dim diagnosis. Here I will mention diagnosis key. Let's create my diagnosis table. Table dim diagnosis coming into picture. And then here I will copy paste my key. And as I always do, integer, and it is my primary key, I will say PK. Now, what else I can store in diagnosis? Maybe diagnosis name. That makes sense, right? Diagnosis name. It is varchar. Maybe he's doing a ultrasound or something like blood test or some other test, right? Maybe he there are also categories for diagnosis, right? Maybe I can mention any serious illness if he's having during diagnosis, maybe chronic flag as a boolean, let's say. What else I can mention here? I guess that's okay. We will expand it if we require that, but as of now, I am okay with this diagnosis. So, where is my diagnosis? Here. Beautiful, beautiful. This is why I love this DB diagram, guys. So it makes my work very easy. I just need to focus on my table creation, and these diagrams are automatically created. And see, guys, it is also running these dots towards my keys. So this is very beautiful. That's why I really love this. You don't need to sign into this. Okay, you can just search it and start creating it. It's a very basic one. It's nothing rocket science here. So now let's come back to the topic. We have our stuff into picture. Now doctor asked him for diagnosis. He even done the diagnosis. Some patients don't need diagnosis, so they will be having null entry here. That's fine for me. What else doctor will be asking? Consultancy timing, right? The patient is going to doctor. This is basic, right? Patient, this is a matrix. So what let me do one thing. Wherever there is a matrix, I will add a note. How to add a note? How to add a note? I guess, yeah. I will add a note saying this is my matrix. Okay. Let's see if it's visible even here. Yeah, I can see metrics. So I am going to add notes for this. We were saying consultancy time. How much time a doctor spent on a patient? Consultation time, let's say in minutes. So I will just say MIN. Oops. This is also my metrics, right? What should be, let's give it a teacher as of now. You can change it. Okay. I'm just giving it for sake of giving it. And this is also my metrics. Perfect. What else? Maybe visit. He visited the doctor. There is also cost. Doctor will obviously asking for payment. Let's do that. Visit cost. What is visit cost? Maybe I will put here something very good here this time. Decimal to maybe $20 something. And again, this is also my matrix. I will give this a note. Matrix. Perfect. What else? What else? What else? What else? I don't think of anything else. So I guess I am done with the patient, because if I think very rationally, patient came into my hospital and he created the dim diagnosis. He created the dim patient, and then staff assigned him or her the doctor and the department. So he gone to that. We know the date when the patient visited. We know the location, which hospital he visited. We know if doctor had advised that patient to go for some diagnosis. We know that diagnosis using dim diagnosis. Okay, that makes sense to me. We also have metrics, visit count, and obviously doctor will asking for the fee. We are storing that fee as well, and the minutes, so that we can see. Why I am storing this consultancy minutes is so that I can see on average a doctor is spending how much time on a patient. That's the only intention I had used the consultation time in minutes. Maybe I can store one more thing here, which is just came into my mind. Wait time, because if doctor is also giving time, then patient is also be waiting right in the queue for his time. So maybe we can also store that. That is also a good matrix to store. Matrix. Perfect. I am not touching this table now. I guess I am done and dusted with my fact visit table. Okay. Now I had created the first fact, and all the entries and all the things are here. So this fact is representing which schema, guys? If you see, it is having a sub tables. This means it is following my Snowflake schema, right? Cool, cool. We had mentioned a lot of good stuff. And now in the phase one, we had customer visited. Perfect. We had fact visit for that. Now there will be some patients who will be going to admit into that hospital because of the diagnosis they had done, right? They found some kind of serious illness in that diagnosis, and doctor recommended that patient that please don't go home, please get yourself admitted right away, right? So let's create that fact also, right? Here only we will create it. I will say table fact admissions. Okay, you can name it appropriately. I'm just naming it admission. And here I am going to store, as always, my admission fact key. If I say admission fact key, and I will say integer, and this is my primary key for my fact. What else I can store? Obviously, the patient is only going to get admit, right? So I am going to store the patient key. I will just copy paste. I had stored my patient key. Perfect. Now, obviously, which doctor asked that patient to be getting admitted, that also is important. So I will store the doctor key, and obviously department also will come hand to hand with doctor. I will also store the department key. And what else I can store in this admission table? Maybe I can store admit date key, because I am having a date column. I can define that key in that date. Maybe I will say admit date key, the date on which he was admitted to my hospital, integer. And see guys, here I am going to define something which we had discussed earlier, which is known as role playing dimension. I am going to copy paste this same one, and I'm going to paste it here. And this date key only is becoming my admit date key. This phenomena is known as role playing dimension. The same dimension, the same column is playing multiple roles, right? Cool guys. So I have my stuff here. A patient is also admitted now. And once the patient is admitted, staff will be checking his diagnosis report. So I'm going to record that as well, integer. And then I will just copy paste my diagnosis from here. Perfect, Jaswinder. Perfect. But why this error is coming? Oh, okay. Anyway, yeah, that is done. Diagnosis key is also defined. See, guys, this my beautiful fact is getting generated here. Perfect, perfect, perfect. Continue. Diagnosis key is getting generated. Okay, patient came, department, and he admitted and diagnosis. Yeah, if he is getting admitted, one day we will discharge that person, right? So I will say discharge date key. Okay, and again I will refer this table only, as it is my role playing dimension. That's the beauty of these role playing dimension. Cool. So now discharge date key is also there, diagnosis key is there. Let's define some metrics also, right? Okay, what metrics there is possible here? Room type, right? Room type is a matrix. Then what else? Maybe admission type, VIP or critical admission, or what kind of admission. I don't think that even required, but let's do it. I had done that. It is also a measure, so I will just say measure or metrics. Now, what other metrics or attributes I can have here? Length of stay. That makes sense, right? I can record this thing, length of stay of that patient, so that it will help me eventually in calculating my capacity or other calculations. So maybe we keep this, and maybe total cost also. Let's keep. What was the total cost beared in all this process? Yeah, I guess that's pretty much about the dimension of admission, because patient came, doctor recommended, he got admitted, he can get discharged. And even though he is admitted in the room, so that also makes sense to me. Admission type is also making sense. Length of stay also and cost is also making sense. I guess that's pretty much about this fact. We had covered the phase one, which was a patient arrives, they see the doctor for the visit, they might be admitted for a longer time. We need to create admissions table. That's the only reason, guys. If you see this picture, I had highlighted this in yellow so that it actually makes sense to you also, that how we can find the words from the description given by the interviewer or someone or the business to create those kind of dimensions. Okay. Now let's focus on the phase two dimensions. For first, I will do is I will just minimize this thing for you. So I hope you understood these two facts, how we created it. Now I am thinking to create another fact that is part of phase two, which is the clinical action. Like obviously, doctor will ask for some lab test or maybe some surgeries during this time. So we need to track all these things as well. So let's create another fact table which will be storing all the lab test. For that, I will again mention table fact lab tests. Maybe I will mention my first is surrogate key lab test fact key for key, and I will say it's integer and it's my primary key. Now, obviously, everywhere, mostly the patient will be doing all these things, right? So it eventually makes sense to store patient key and doctor key and department key everywhere. So I will just copy these three and I will just store it here. So I have patient key, doctor key, and department key. Now, obviously, on which date he had gone for lab test, that is also important. And I will store that. I will just copy paste. I will not store. I will copy paste. Where is my date key? Here it is. Just copy paste this. Perfect. I have my date when the patient had done his lab test. And maybe we can also store the procedure key for which procedure he is doing the lab tests. That's the reason I am going to create this procedure key. Table dim procedure, and here I will just mention the procedure key as of now. Okay, I will just integer pk. We will fill this afterwards. Okay, procedure key is there. Now let's also put some measures, like let's put test result value, maybe positive or negative or whatever there is observation. And what else? Maybe to test cost. Cost is very important, right? So I will put that cost here, the lab cost, and then maybe test count, how many tests he had done in this time frame. Okay, maybe I can mention something as default one, that one is the default one. So I have my lab fact also ready. I guess these are the only things which we usually do in labs. Like patient is going, he is doing his test, so he's paying the money, and we can store additional information like procedures, and we can also store this test count as well. So that's fine, that's up to you guys. So I had stored it. There might be other columns, so I assume you can fill those out. So I have fact lab test ready. What was the other fact? Surgery, right? So he had done the lab test. Now he might be requiring some kind of surgeries or some kind of operations. So I will create that fact also. I will just say table, you can say fact surgery or operation. I will just say surgery, and Then I will open curly braces, and as always, first we will be defining our surgery fact key, which is integer, and this is my surrogate key for this. And what else in surgery? Also in surgery, same thing, same story will repeat, like patient key, doctor key, department key, date key. So I will just copy paste them here. This story will repeat everywhere: patient information and doctor information. Now, instead of these, what else? Now, procedure key will come into picture, guys. Which surgery he is doing? Okay, that is the procedure. So I need to mention something in my procedure table as well. I will mention procedure code, I will mention procedure name, and then type of procedure. And then obviously I want to store the standard cost for each and every procedure. Now we had the procedure key in my surgery table. What else I can define here? Maybe I can define the duration of the operation and cost of the operation, right? And maybe the even this is also possible that the operation was a failure, right? So maybe I can define duration. I will say integer or date, whatever time, it's fine. And then maybe surgery cost, surgery or operation cost, whatever. And I will say decimal and something whatever. And then I will say success. Mm, this is also possible, right? That operation got failed, so I want to record that success rate also. And maybe there is some complication happened, like maybe some death happened or some other scenario happened, some kind of issue. So I want to record the complications because that is also possible. Yeah, I guess that's pretty much about my fact surgery. So my fact surgery is ready. We are done with phase 2. Okay. What is phase 3? Phase 3 is a resource and medication, because someone is done with his operation. Now he needs bed rest and proper medicine. So let's first create a pharmacy fact. For medicine, he needs to go to pharmacy, right? So that's why I prefer to name it as pharmacy, or maybe we can name it medicine, but let's name it pharmacy. Okay. What comes in this pharmacy table? Obviously, first is pharmacy fact key. Then I will mention the details which are default details. As we already know, all these 4 columns, I will blindly copy paste, right? Perfect. And then what else? Now in pharmacy, we have drugs, right? So I want to create another table which will be having the details of drugs, because that's the pharmacy work, to store all the medicinal details, right? So they need a table where they have all the details, all the cost of the medicines and all those things. So I will define a drug key, and I will say integer, and I will refer this drug key to dim drug. And now I need to create this table. This table I am not going to create in very detail. I will just create 2 3 columns. This is my integer and primary key. And then I will store drug name or medicine name. And then I will store drug cost, maybe category, like blah blah. There are a lot of columns we can store here. And I will just say other columns, other columns. Perfect, perfect. I have my drug key defined. I have other things. Now let's store some measures, right? Measures is also important. Quantity, and then unit price, and then I will store total price also. Let's store that. Total price, decimal 12,2. Perfect, perfect. This is done and dusted. I had created the fact pharmacy. I guess these are the only details required. Second table was obviously after the operation, patient needs medicine, but he also need a bed to take rest. So I also need to provide those patients bed, right? That's my business, right? I will create a fact table, right? Table, fact, bed, occupancy. Let's say this name, this big name. And here also I will say bed, fact, key, which is integer, and this is my primary key. And then obviously I will just copy paste all these four as I always doing. Copy paste. Now let's think what else I need in this bed occupancy table. Obviously, first thing I am thinking is bed ID. I need this column, right? This is my attribute column. So I will say bed ID varchar. And then I also need bed type. Don't you think? We need to know, right? So what type of bed he is, and maybe occupied flag. There is a possibility some of the beds in hospital are empty. So I need to know which beds are empty so that I can allocate those beds to the other patients, right? So this is my phase 3. Okay, my phase 3 is done, guys. As per me, we had created all the required things in phase 3 pharmacy and bed occupancy. Now the phase 4 is saying to generate the bill for those patients, right? Obviously we need to generate the bill. And after bed, after pharmacy, the patient now is healthy, so he wants to go home, and we will be discharging that patient. And before discharging, we need to ask him to pay the bill. So we will be creating that bill table as well, and that is going to be my final fact table in this. Let's quickly create that. Then fact, billing, and when it's come to billing, again I will just say billing fact key, and I will say it's my integer and it's my primary key. Perfect, yes. And then I will copy paste few details as I always do. And then I need to think here, because there are some patients which had opted for insurance. So in that case, I need insurance key so that I can go back to insurance company and ask for the payment. So I need to create one more table here, which is dim insurance, and I will mention here insurance key. Whenever you are going to build a dimension model, always start with facts, right? It is very convenient. Insurance key, integer, and then this is my primary key. Perfect, perfect. I will not be mentioning any details. You mention it. Okay. Other details. Now, insurance. Okay. The person who is insured, he will be having insurance key. And now, the person who is not insured, I want to know that person first. So I will say insurance covered flag. Even he is covered or not, right? I need to generate bill for that patient, right? So I will say insurance covered flag, Boolean, insurance covered flag is there. Based on these things, I need to create some measures. First is gross amount. They need to pay the bill, so they will should know their gross amount. And then they also need to know who is payable. Okay, if maybe insurance company is payable, maybe a patient is payable, and is there any discounts we are offering? That is also a pretty good thing to capture. Is there any discounts, and what is the net amount? In case of insurance, the net amount will be paid by insurance, so for patient it will be zero. But for those patients who are not insured, they need to pay this net amount, right? So this is pretty much about the fact billing, right? With that said, we had created all the facts and all the dimension. This is the complete hospital dimensional data model. Let's now write queries and see these metrics in play. I had written down the 5 scenarios in one tab where I want to calculate the total patient's revenue by month, average consultation time by doctor as well as department, and then I need top 3 doctor by number of patient visits, and I need the revenue contribution. Let's start one by one. I will first start with the total patients. In order to calculate the total patients visit by department, which two tables I need? First, obviously, I need the fact visit table. Secondly, I need department table, right? So I will join these two tables and I will do the required aggregations to calculate this total patients. Okay. In order to do that, I will just say select, I will do some enters and I will mention my first table, which is my fact visit table. And I will join the fact with my department table because that's how I can calculate the total patients by department. So I will say to join this department table on the basis of department key, right? So I had joined it. Now I need to pull the columns. Which columns I can pull? I need total patients and I need by department. So for sure, I need department name. So I will say department, name. That's for sure I need. And I will just name it as A and B so that it will be easy to understand and even query will not be causing any kind of ambiguity. So I had pulled the department name. Now I just need to calculate the total patient. Now I will just say count star and I will say just as a total visits. And as I had done the aggregation, I will group by the department name. And my first scenario is done and dusted. Perfect. This is my first scenario. Now, what is second? Second one is revenue by month. Okay. Here I need to calculate revenue. In order to calculate revenue, which fact I need? I need fact billing, right? That is where we had stored all these revenue information, right? I need to calculate revenue based on the time frame, right? So I also need dim date into picture. This is my fact billing table and this is my dim date and they are joined based on the date key. So I will also do the same. I will say from fact billing, I will name it as FB and then I will join this with dim date and I will say DA and I want to join this based on date key. Cool. So I had applied the join. Now I need to know the revenue. In order to know the revenue, I need to do the sum of this net amount column, which is there in my fact billing, right? So I am going to pull this column. So in order to pull this column, I will say FB dot net amount. Okay. This will give me my revenue. And now I need revenue by month. So I need to pull month column from the dim date, but I also need to pull the year column, right? Because in that way, I will be discussing which month of the which year this revenue came, right? So I will pull two columns from this dim date. First is month and second is my year. And then I need to calculate revenue. I will just do sum of this net amount. And as I had done the aggregation, I will just do group by and I will mention these two columns and this query is also completed. That's it. Cool. Now the third question is average consultation time by doctor as well as department. I need to calculate the consultation time. Which tables I require here? First, I require my fact visit table because this is where my patient's information is there. Then only I can see the consultation time. And I will say FB. Then I need to join this table based on doctor as well as department. This is my fact visit table and this is my dim doctor table and this is my dim department table. I am going to join fact visit with dim doctor based on doctor key. And now I need to calculate average consultation time. As you can see, in fact, I am having the consultation time in minutes. What I just need to do is I just need to do select and then I need to just do average of this time. Consultation time in minutes. I will just do average and I will say this as average time. And then I need to do this by doctor as well as department. So for sure, I need some information from doctor table and I will just pull here doctor name. And I will also pull my department key from the same table. If you need the department name, then I need to join this with my department key table. So in this case, I am going to join this. Okay, let's join that. I will pull from department table, I will pull department name, let's say. And in order to pull that, I need to join this. So I will join this dim department on the basis of department key. Now I had done pretty much about everything. And just one thing which is left is I had done aggregations here. So I need to group by based on these columns. So I will just mention these in group by, and with that my query is completed. Cool. Now the next question is I need to calculate the top 3 doctors by number of patients visits. In order to do that, I need to first obviously need the patient visit data. I obviously need dim doctor. And here I need top 3 doctor. In order to do these kind of things, we usually use window functions, right? So here I will be using the window functions to get the top 3 details. So first I will start joining these 2 tables. I will just say join my fact visit table with this doctor table on the basis of doctor key. Once I had joined these, I need doctor name because top 3 doctor. So I will be saying I will be writing doctor name, and then I need number of patient visits. So I need to calculate the visit counts, right? So in the fact visit, I am having a column called visit count, right? So I will just mention that column here, and I need total. So I will just say fv dot visit counts. In this way, I got the visit counts as visits, let's say, and I have doctor name, I had my visits. Now I need top 3. In order to do top 3, I need to use aggregate functions. So I will use rank function here, and I will say rank over order by this one because I need top 3. So I need to order by this one. And then I need in descending order. So I will put descending and I will say it as rank. And on top of that, I will write another query like select doctor name and visits from this table, which is now my subquery where rank is less than equal to 3. This query is very dynamic. If you want top 3, you just mention 3. If you want top 30, you can just mention here top 30. If you want top, let's say 10, you can mention here 10 and your work is done. Cool. This is my fourth query. Now let's come to the final query. Final query I need to analyze from this data model is revenue contribution percentage by department. Whenever there is revenue, I need to go to my billing table, isn't it? So here is my department table and here is my fact billing table, and these are joined based on department key. And now I will just write here fact billing and I will join this with the dim department on the basis of department key. And now I need to pull a couple of columns. And first I need by department. So surely I need to pull the department name. So I will say department name that is coming. Now I need revenue contribution. Okay. What columns I can pull based on this? I need to do the sum of this net amount to get the sum all the revenue based on department. So I will just say sum of this net amount as revenue. Okay. And I also need to calculate the percentage of revenue based on department. So I will say sum of net amount. And then in order to do this percentage thing, I need to multiply this by 100. And then I will divide this whole thing by the complete sum of this table, right? Because here I am doing aggregation and I will be doing group by based on department name. Let me mention that first. group by this department name. So I need to have the sum for whole data so that it can calculate me the percentage. So I will say sum of sum inside of this one. So this will give me a sum of whole data, and I will say over, and now I have the complete sum here, and I can say this as revenue percentage. That's it, guys. This question is also completed. And with that said, we had completed dimensional modeling. And thank you so much for watching this video. Have a really nice day. Bye bye.